Hey guys, so in this video we will continue what we did in the last video and talk more specifically about the energies of these different subshells. As you remember, the energy has to do with the quantum numbers n and l. So the 1s, 2s, 2p, 3, those will all have different energies. And so the first thing that we'll do is talk about how we can rank their energies. And so in general, there are some exceptions, but in general, this is how we rank the energies. So I'll have energy going up. Okay, so down here will be the lowest one, and then we'll go to higher energy. So a higher n, hopefully, would make sense. A higher energy level means there's going to be more energy, just as we talked about in Bohr's model. And you'll notice a little difference that in this model, the energy also depends on a second quantum number, not just n. And so that's a difference that we'll touch really in section 6 about one of the ways this quantum model differs with the Bohr model. Although in hydrogen, some interesting things do happen because there is only one electron, but we will talk about that later. So ranking these energy levels, or ranking the energies of the subshells, we start with 1s. 1s will have the lowest energy. The next lowest energy we will have is 2s, and then 2p, then 3s, and then so 3s, then 3p. But we don't go to 3d. In fact, 4s has a higher energy than 3p, but a lower energy than 3d. Okay, so it doesn't rank really directly. So there's a little bit of mixed matching going around between the energy levels and the subshells. Okay, so then after 3d we have 4p, and then 5s, and then 4d. And then after 4d we have 5p, 5p, and then we will have 6s, and it's after 6s we go back to 4f. Okay, so the f subshells will have a lot more energy, even more energy, right, than 6s. 4f will have more energy than 6s. So I'm not going to talk about why it's in this order. It's just we know it's in this order, and in fact we can see it's in this order using a technology called photoelectron spectroscopy. It is it's more of an experimental method. And photoelectron spectroscopy, PES, you can learn about that in the link in the description. That's one of the ways that we actually have experimentally shown that this is true, that with all these subshells and the number of electrons, that we can actually experimentally show that through photoelectron spectroscopy. Also, it just so happens that the combination of quantum numbers that we talked about do produce perfectly the periodic table that we see in nature. And that's why I've got the periodic table here, and we'll talk about that in a minute. Okay, so we've talked about the notation NL, right, for the subshell. And now there's one more thing where we'll have in the notation, this is called Electron Configurations, where we will write it as, let's use this color, NL, this is the subshell, and then the number of electrons. So NL, and then the number is it looks sort of like an exponent, but it's really just a superscript. Okay, so let's look at an example of this, what I mean by the electron configurations. And so we'll see this using the example of tin. And if we find tin on the periodic table, it's right here, element 50, Sn. Okay, so, and then I'll show you how we'd write these electron configurations. So let's use Sn as our example, and this is Sn neutral, right? So it's going to have 50 protons, which is the definition of tin, but we're going to say it's neutral, so it is going to have, let's see, 50 protons, and then it will have 50 electrons, because it's neutral. Okay, and the electrons are important. Okay, So let's write out the configuration, the electron configuration for tin. And so what this will be doing is essentially assigning quantum numbers to all of the electrons in tin, but it's sort of a shorthand way of doing it, although it will be pretty long for tin, but then we'll see really even a shorthand of how we can do that. So the only other thing we need to know is that electrons will naturally go to lower energies, right? So we're going to want to fill up these lower energy levels. So like 1s will get filled up before 2s, which will get filled up before 2p, right? So these will all be filled up. We'll fill up these before we can move on to the next energy level. Although remember, there is a limit to the number of electrons that we can have in each subshell. So only 2 electrons per s subshell, 6 per p, 10 per d, 14 per f. Okay, and so we want to start with the lower ones because electrons will naturally have lower energies. This is called the ground state, which means the lowest possible energy. So we are filling up the lower energies first. So what we'll do is we'll essentially assign each sort of group of electrons at a time. So I'll switch to this color. So the first electrons, right, we'll first have to fill up 1s, and that will be 1s2. 1s2, because the 1s subshell, 2 electrons, so 1s2. Then we move on to 2s2. Okay, so we've gotten the first 4 electrons assigned, right? So we have 2 electrons in 1s, 2 electrons in 2s. Then we'll have 2p6, 6 electrons in 2p. We're still only at 10 electrons, so we're going to have to keep going until we get to all 50 electrons. So I'll go for a little bit more, and then we'll stop to count. I've got it written down already, so I know I won't go past. So 2p6, there will be 2 electrons in 3s. Then we'll have 3p6, and then 4s2, 3d10, 4p6, 5s2. And if you were to count all these up, add up the number of electrons, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2, you'd get 38. We have 38 electrons assigned so far, so we've got 12 more. So let's go. Our next one is 4d10. 4d10, and that takes us to 48. And then after 4d, 5p. And how many electrons do we have? Well, we only have 2 left. Okay, so the outer electrons, which will be called the valence electrons, are 5p electrons. They have a quantum number, the principal number 5, azimuthal number 1. And there are going to be 2 of those electrons. So this is the electron configuration. What it tells us is if you give me some energy, so say the energy 3p, right, because each of these correspond to a certain energy, 3p, which in the 3p subshell there are 6 electrons. We can see that. In the 5p subshell there are 2 electrons. So we can do this for every element. And so that's just an important thing for chemistry. So essentially the point of this video is just showing a use for the quantum numbers that we have and how this actually shows the periodic table. Because the periodic table is about how elements react with each other. And when elements react, they really what's reacting are the electrons. It's about the electrons. So the periodic table is set up, right, in these periods with the vertical columns having similar electron configurations, similar outer electron configurations, because the outer electrons are what are really important in chemical reactions. So if you have, 5p2 at tin, in fact, carbon, silicon, germanium, tin, lead, and quadrium will all have 5p2 as they'll have 2 electrons in the 5p subshell. And so those outer electrons, so these will all behave fairly similarly, not 100% similarly, but these will all behave fairly similarly in chemical reactions because their outer electrons have the same quantum numbers. 5p2, actually not 5. It's really the p2 that's important. So this will be tin will be 5p2, lead will be 6p2, germanium will be 4p2, and you can actually see how we'll figure that out, because the periodic table is split up into blocks, with the exception of helium, which in this case helium really does belong over here, although it is here listed here for a reason. But just for this purpose, I'm going to put it here, because what's really important in an electron configuration, everything below 5p2 is going to be filled up, right? If the outer electrons are 5p2, it's going to be 10, right? Because everything else is filled up, right? So what's really important, especially in those chemical reactions, are those outer electrons. And we can look at different blocks of the periodic table. So this block right here, and I'll put this right here. This block, this is the S block, okay? Now in here, I'll put in blue. Actually, it kind of goes down here. It's a little messy down there. But this is the P block. Here we have the D block. And here we have the F block. And the F block really goes right here, right? That's where it is. It's just they didn't want to extend the table to be too long, so they put it under. Okay? And this tells us, hopefully you can see the F here. What this tells us is the letter belonging to the outer electrons. And then there are numbers here. So this row, for S and P, this row is 1. We've got 2, 3, 4, 5, 6, 7. Similarly here, this is 2, 3, 4, 5 down here, 6, 7. And so you could actually see very quickly here, the outer electrons for tin, it's 5, P, and then we've got 1, 2, 3, 4, 5, 6. As you see, the P block has 6 in each row, the S block has 2, D block has 10, F block has 14, because that's the number of electrons. So for example, if we were to look at europium, right, first I'll write the numbers here. In fact, for D, it doesn't go to 4 because it starts at 3, because then you have 4S, and then 3D. So 3, 4, 5, 6. Now this is a little bit messy. Here you start with 4 and then you go to 5. So it's a little bit messy, but in general this is sort of how it works. So if you have europium, element 63, the outer electrons will be 4, F, 1, 2, 3, 4, 5, 6, 7. So 7 electrons in the 4F subshell. And so that's sort of just a shortcut, and it also explains why the periodic table is how it is, because each of these rows will have the same number of electrons in the in a certain subshell, in the S, P, D, or F subshell, and those shapes that will really determine how they will interact, how their outer electrons are structured in the atom. So hopefully that makes sense. Again, this is chemistry, and I know I'm kind of going quick and a little bit messy, but really the big point is that this quantum mechanics stuff, these quantum numbers that we will derive by the end of this course, give us the structure of the periodic table, which tells us how all matter that we deal with around us, how that interacts and how it forms bonds and chemical reactions and makes, you and me. It's all based in this periodic table, which is based in the quantum mechanical principles that we will be deriving throughout this course, right? So really, we will be showing how the periodic table works by the end of this course, which I think is pretty cool. So with that, I will see you in the next video.